it's loading. I will also make a backup there.
Okay, I can confirm that it's working.
Okay, then it's the okay. So hello everyone. So today's session will be about the following theme: renormalization and disorder, studied via a simple toy model. And for the first talk, we have the pleasure to hear Bernard Derrida from Collège de France and École Normale Supérieure in Paris. So we are listening to you.
Okay, thank you. So thank you for the invitation. And here today I'm going to report about some work which has been done over the last few years. And it started, okay, so I don't see how. Yes, so it started with some work with a student, Martin Retaux, in 2014, and then Zhan and other people, Shen, Wu, Lifshitz, Daga, joined the project in some way, in the sense that they tried to prove the kind of results that we had claimed, or the kind of results we claimed in this earlier paper with Martin Retaux. And then there were a few results which appear in this list of references. I should mention that here I am going mostly to talk about the discrete time version, but there is a continuous time which was also studied by Hu, Malin, and Pain. Malin is one of the organizers. So these are essentially the main references related to this work. So the outline of my work will be, first, I will try to say why we studied the toy model. So in order to understand the toy model, you don't need to know why we were interested in this particular model, but I want to motivate it. So this will be the first part of my talk. Then I will discuss the toy model, the claims, and the results, and then we'll be more precise about how the results the proof were obtained. And then I'll come back towards the end to the motivations and why the problem, what it can say about the problem, original problem we had. Okay, so I am not sure that people are very familiar with the idea of renormalization and the Harris criterion, so I am going just to mention it briefly, but when we come to the toy model, this knowledge is not necessary. So what is the idea of renormalization? I guess most people have heard about the problem of percolation. Percolation, you have a lattice, and then you have sites which are either occupied or empty with probability P, the site is occupied or empty. And if you imagine that you have a large system like on the left, then you would like to know whether this large system could look like a smaller system with a renormalized parameter P prime. So how can I make these two systems equivalent? For example, I can decide that the probability that the two sides, the two red sides are connected is the same in the two systems. So if the probability of the system of the left with parameter P for the occupation number is the same as the probability that the two sides are connected with probability P prime, I say that the way to renormalize the probabilities P prime is a function of P, and then if I know this function, I can tell that the phase transition, okay, in principle, I would like to know this function for a very large system, but if I can tell what this function is, then the phase transition will occur when I find a fixed point, and in a more general way, the idea of the renormalization is that if you have a system which is characterized by a certain number of parameters, and then you can show that the system has some properties similar to a system with a renormalized parameter and a smaller size, if you can write the way the parameters are transformed, then usually the phase transition is given by the fixed point. And then if you linearize near the fixed point, you can understand the critical exponent and the universal behavior. So really, this is the idea of the renormalization group. Okay, so it will appear in the toy model, and that's all I want to say about the renormalization group, which is, I guess, known for many people already. Now, the second aspect which motivated to introduce this toy model is to look at the simple model of disorder, and this model is called the Polancharaga model. And the Polancharaga model is a model which describes how two strands, for example, of DNA get unbound at a certain temperature, for example. So you imagine that you have a certain binding energy for all these bonds there, and then there are loops, and at high temperature the loops win, so somehow the two strands become free, and at low temperature the binding energy is strong enough so the two strands stay together. And the problem is totally equivalent to another problem, which is a problem of deepening. So you imagine that you have a line like on the bottom here, and this line has some contacts along the horizontal axis. Each contact gives a certain energy, and then there is an entropy for the loop. So this is what is called the Polancharaga model. And for this model, the question is fully characterized or defined by the following in the following slide. And so you imagine that each time the line has a contact, there is a contact energy that I call xi, and this xi depends on the position I. So if you have a contact at I2, then it will be an energy xi2, and they are independent random variables. And on top of that, each loop, which is a loop is just between two consecutive contacts, gives a weight which is given by this formula, Wn s to the n over n to the c. Now, it turns out that the very important parameter here is the c, the power law there, and the exponential factor does not matter because the quantity we are interested in is a partition function, which is written down there, and you can check very easily that if you put this s parameter, it will factorize, so it has absolutely no effect, so you can choose it to be 1. Okay, so this is a Polancharaga, and the difficult part is that you would like to know what is for large L this partition function, and when the xi are random. Now, it turns out why you are interested in this problem is that it looks like one of the simplest disordered systems. First, because if you look at the situation, which is a pure system, which is, okay, so before I say that, so you want to say something about this partition function, and you want to know it in the large L limit when the system size becomes large. And in the large L limit, you expect that there is a phase transition between when beta is small, so the binding energies are small, then essentially the sum will be dominated by one loop or a very few number of large loops. And as a result, F infinity will be 0 because essentially the beta dependence will disappear in the large system size limit. So somehow if beta is small enough, then F of infinity is 0. And if beta is larger than a certain critical value, F infinity is non-zero. And really the question is, okay, so let me see. The question is how you start, what is the shape of this curve near the phase transition? So really this is the question we have about the Polancharaga model. Now, why the problem is a priori simple? It is because in fact, you can solve very easily the case, the pure case. What we call the pure case is when all the xi are the same, then you can tell what is the critical temperature beta C, or the critical parameter beta C at which the phase transition occurs, you can show that if the parameter C, so maybe you remember what C was here the parameter in the loop here. So if the parameter C is larger than 2, the phase transition is first order. If it's between 1 and 2, it's second order, and with an exponent that which is 1 over C minus 1. So it tells you the shape of this function. And in fact, if C is less than 1, there is no phase transition. So it's not the case I would consider. And the question is, what happens now if the xi, if the contact energies are not all the same, but they are random? And we have in mind not a very general situation. We have in mind already we would be very happy to be able to tell what happens if the distribution of the xi is narrow. And the question is, what is the phase transition? So we can, for example, ask whether the F infinity at the phase transition will start with a singularity beta minus beta C to the power 2 minus alpha. I'm sorry to call it this way, but this is the way the physicists call it. And in fact, it has been shown in a number of papers. So here there's a list of many contributions, but already when C is between 1 and 3/2, then if the disorder is weak enough, then essentially the pure system and the disordered system behave the same way. So the transition is the same. But one, I think probably the most important result on this subject is that Giacomini and Toninelli proved that if C is larger than 3/2, essentially the transition has to be always smooth. And this means that the alpha pure should be larger than the alpha disorder, if there is any alpha disorder, because what we mean by smooth is that the second derivative of the free energy is continuous, and then so it's not possible that the pure and the random system behaves the same. And there has been a number of discussions what happens at 3/2, but in fact, we had a conjecture many years ago with Hakim and Vanniminus, and this has been proved that also when C is 3/2, then again, the disorder is relevant. And so you imagine that the pure system and the disordered system behave in a different way. And there has been some work by Tang and Chate, who are physicists, and they give some argument to say that, in fact, the phase transition is not a power law, like what is shown at the top of the slide, but rather it's an essential singularity, an infinite order transition. So this is all my introduction. Now I am going to talk about the model itself, and maybe if some of you are not familiar with some of the things I discussed so far, it's not important to understand the toy model I am going to discuss now. Okay, so this is the toy model we consider, and in this paper with Roto and in later papers, and it's the following. So essentially you have a kind of tree, you have some infinite number of random variables at the top of the tree, x0, x1, and so on. And what is given is a distribution of these random variables. And then so this is, for example, the index 0 is like initial time, and then time increases, and to get the value of the variable at time n+1, then you just take two independent realization at time n, and then you combine them, you add them, -1 and 0. So you take the maximum of the sum -1 and 0, and that's it. And then the thing you are interested in, so if you want to make the connection with the model I mentioned before, the Polancharaga, essentially what you have to, the equivalence would be to say that the length of the polymer before, or of the line before, would be 2 to the n, and the free energy would be this number xn. Okay, and the main question is, what is the limit of xn over 2 to the n? and what is the phase transition of that? So this is the full model, and this is the question you ask. And so this limit, of course, will depend on the initial distribution P0. So just to repeat what I said, is that you imagine you have this very large tree, and each node, the variable is obtained by combining the two variables at the previous generation, and then you take the max of xn1 plus xn2 minus 1, and that's at the max with 0, and that's it. So this is the full definition of the model, and you want to know what is the limiting value of xn over n for very large n. Now, in this case, the pure case is somehow trivial, in the sense pure means that the xi do not fluctuate. So if all the xi are the same, then it's a very easy thing to do. And then you find that if all the xn initially takes the value mu, then y will depend on mu in the following way. And so it's constant, is 0, and then it will start linear. So there is a phase transition. For a physicist, we will call it a first order transition. And now, if the initial distribution is broad, so here, for example, I take a two-value distribution which consists of two delta functions, one at 0 and one at mu. If you vary mu, so imagine, for example, that lambda is fixed, or you could change lambda and keep mu fixed as you prefer. Here, I have drawn the case where lambda is fixed. For example, take lambda equal 1/2, and then you change mu, and at a certain value, there will be a mu critical, and the main question is how it starts. What is the singular behavior you have here? Okay, so this is really the question, and this is the question for which we got a certain answer. Now, why the problem has to do with renormalization, and in fact, the full problem, you see, the thing is that you start with some initial distribution, and when you go down the tree, then the distribution of the variable x is modified. And so if I give you P0, in principle, you can compute the probability of x1 and then the probability of x2 and so on. And it turns out that you can do it in a very simple, you write it in a very simple way, in the following way. That is, if you take the generating function of the variable xn, and then you call it hn of z, so this is a generating function, then you can show that the recursion is nothing but this recursion on this generating function. So somehow for people like me who have worked on the renormalization group, you are very happy because you have just a function, you have to renormalize this function, and then you have to ask what happens when you do these iterations many times in the large n limit. Okay, now let me just tell you what you can tell about this recursion on the generating function of xn. And the first thing is a result which is almost 40 years old by Collet and collaborators, and tell that there is a phase transition. So there will be a phase transition. And if I take an example, for example, if the initial distribution consists of two values, x take value 0 or 2, with these weights, 1 minus lambda and lambda, then their claim is that lambda c is 1/5. In fact, they can tell for any initial distribution what is a phase transition. But just to tell you that for this very simple situation, lambda c is 1/5. And this 1/5, I would say it's far from being trivial. You see, if you think about the problem, why is it at 1/5? It doesn't, okay, it's not obvious a priori if you have not thought for some time about the problem. But okay, the other thing I want to say, which is surprising for me from the point of view of the renormalization group, is that you have this recursion for the distribution, and so you could say, as usual with the renormalization group, you want to try to find the fixed point. So is it possible to find a fixed distribution. So you would say that Hn is equal to Hn plus 1. You try to find a fixed point. And in fact, it's easy to see that if you choose whatever you want for H0, then you find a fixed point by solving a quadratic equation. So you can find fixed point. But the problem is that none of them is interesting for this problem, because when you analyze them, you find that they don't correspond to positive measures. So it's what Zhan told me, it's called sign measures. So this means that some of the weights become negative. And so certainly it's not something you are interested in this context. And in fact, it turns out that all these fixed points have no interest, but the problem has a phase transition, and the phase transition is of the type of the Berezinski-Kosterlitz-Saules type. Okay, so let me just say what are the claims. The first thing is that Collet and collaborators could prove, in fact, is that the phase transition, you see, that will be very important for, in particular, for the proofs that Zhan will mention, I think, is that it turns out that for this problem, the location of the phase transition is known exactly, and this is this work by Collet and collaborators, and they say that if you take the initial condition, H0, and it will be given, you will be at the phase transition if the initial distribution satisfies this relation, 2h'2 minus h2 is 0. And in this particular case of initial distribution, which consists of 2 delta peaks, then it gives you 1/5. Okay, so that's a very nice thing compared to most of the disordered systems where you don't know where is the phase transition. Here you know it. Now, if you are not at the phase transition, so if the difference is not 0, if you are close to the phase transition, then it turns out that if this combination 2h prime minus h is negative, then you are in the phase, the limit is 0. So this is, you can prove. And the claim was that if it's positive and small, then the limiting value, the critical behavior is just exponentially small of the kind of the Berezinski-Kosterlitz-Saules phase transition. So this is a claim we made with Damien Reto in 2014 about this problem. And then this was essentially proved later. So let me tell you soon what are the things which have been proved about it. Okay, now you see, as a physicist, when we have a claim, we like to make some simulations to see it. And in fact, it's rather easy to see it in the following way. You see, if you expect that this limiting value, this critical behavior, is exponentially small, if you take the log and the inverse of the square of the log, it should be linear. And so what I draw here is, as a function of lambda, I draw the inverse of the square of the log. And this means that this quantity, when lambda varies, should vanish linearly. And these curves correspond to various xn, increasing values of n. So it's, you see, when lambda, the way it seems to go to 0, it seems to be linear. So it's really convincing, I think, numerically that this behavior is observed. And on the other hand, if you would imagine that there is a power law, the quantity vanishes like a power law, the same data shows this curve. And you see, if you had the power law, then you should see a straight line. And in fact, there is no evidence at all of a straight line. So somehow the numerics seems to support the claim and to exclude any power law. Okay, now let me come to what has been proved. And you see, in fact, that I find very interesting because it's some kind of exchange between claims by physicists and by mathematicians. And so what happened is that Zhan and many other people, Shen, Yu, and Lifshitz, then they tried to prove that this behavior was indeed the right behavior. And so they started with a distribution which consists in a peak at 0 plus something arbitrary. Okay, in order for the thing to really, for the analysis to work, it was important that the values of the random variables are integers. Okay, maybe I did not mention it earlier, but it was important that but this showed that indeed the behavior is what we had predicted. Okay, here there is a small o of 1, so this means that it cannot guarantee that it's just a constant there, but essentially they predicted the same behavior, but there was a condition that the initial distribution should decay fast enough. And fast enough means it had to decay like something like 2 to the x, this power, this exponential, but it was very important to know what the power law in front, and it was important that it would decay faster than x to the 4 here, okay? And what also they could prove is that if this is not satisfied, they could say that there is also a prediction of the same kind, but with the 1/2 replaced by nu. So if there is a decay like c to the x to the gamma times 2 to the x, then it's no longer 1/2 in the exponential there, but it's 1 over gamma minus 2. Okay, so this is the main result. And okay, and so I think this is what Zhan will discuss. Okay, now what you see, when they came with this idea, then there was the question whether one can understand it using the same ideas that we had used with Martin Retaux. And in fact, it turns out that this can be done, and in the following way. So what we did was to start with some initial condition, which was a very, very special kind. So essentially, we started with some initial condition, which was very big. Almost all the measure was concentrated at x equals 0. And then the remaining was very broad and changing very slowly. So essentially, we had a small parameter epsilon, and we said, let's start with a certain distribution, which is of this form here, where R is a certain function. Now, so n is the number of iterations, somehow the time, and x is the value of the variable. And so when you assume a certain distribution of this kind, then you can show that when you do one step of iteration, you remain with the same kind of function, and the function R evolves according to this differential equation. So this is like a kind of coalescing coalescence problem. So the question is whether one can say something about the evolution of the function R, the evolution in time of the function R of this kind. But this is still a difficult problem, but like in the case of what Collet and collaborators have done, one can tell where is the phase transition, and the phase transition is that the place where the integral of R is 1. Okay, so this is a very simple problem also to pose, is to say, okay, I give you some R initially, a function at n equals 0, I give you some R, and then how does it evolve? And it evolves according to this equation. Now, the thing really we did with Martin Retaux was to say, try to look at it, and then what we could do is to find an explicit solution of this equation. That is, if you start with some R, which is an exponential, a single exponential, it turns out that if you put it in the equation, then the exponential, the single exponential remains a single exponential. So the only thing you have to do is to follow how the prefactor A and B evolve in time. So you do that, and if you have learned physics, and especially if you have been able, he had the opportunity to teach it, then you realize immediately that these are the equations that were written by Kosterlitz and Saules to find this the phase transition for the two-dimensional XY model. So you make the connection, and somehow you can very quickly predict the behavior. If you don't know it, then it turns out that it's not so difficult to integrate this equation, and then you find that the R as a function of time is just a pure exponential, and you can tell what B and A are, and then from that you can extract the critical behavior. Okay, so this is, and in fact, the paper also that Hu, Malin, and Pin wrote also, they studied the case where there is a single exponential. Now, it turns out that mathematically, there are many other solutions. One, for example, one family of solutions is that if you don't take a single exponential, so you see, I am just analyzing the evolution of R, which is there, but if you start with two exponentials or n exponentials, and if you do that, it turns out that, again, the function remains a sum of n exponentials, and the way that the parameters evolve is given by what you see it here. So the evolution of BI and AI. So essentially, you can solve the problem. The difficult thing is that to see the full evolution is difficult. We have done some results in the case where we have two exponentials. And what comes surprisingly is that when you start with two exponentials and you are on the critical line, then what happens is that one exponential wins and the other one dies very quickly. So essentially, the solution with a single exponential seems to be an attractor for the situation where you start with many exponentials. Somehow, the one which decays slower wins and all the others disappear. So we could see that when n is 2. When n is larger than 2, numerically this is what we observe, but I cannot say that we could prove it. On top of this sum of exponentials, you have also some solutions that you find which are unphysical, like, for example, the one which is at the bottom, because it corresponds to R, which can change sign, and so it's not very interesting from the point of view of the problem we studied. But okay, these are a number of solutions, and all these solutions, at least the physical solutions, when you take sum of exponentials, they reduce to the case where there is a single exponential and somehow lead to the same behavior. Now, the thing, you see, motivated by the claim that when there was this gamma, the decay was slower, there were over behaviors, then we try to find these over behaviors, and we realize that, in fact, this equation has not as a whole family of scaling solution of this kind. So if you say that you choose R of the form which is there, 1 over t squared g of x over t, you put it into the equation, and you find that the g should satisfy a certain equation there. The exponential is one of the solutions, but there are many other solutions. In fact, if you give the value of g of 0, any value of g of 0 will lead to a certain solution of this equation. Okay, you can write, it's somehow easier to work with the Laplace transform of g. So if you do that, you write an equation. Because we were lucky, we can tell exactly what is the solution in terms of Bessel functions. It does not matter so much, but it turns out what we find a whole family of solutions which have a certain decay gamma. So you see, let me come back to that. So we have this differential equations there. If we look for a scaling solution, we find that for any choice of g of 0, then you have a solution. And if I write G of 0 on the form gamma times gamma minus 2 over 2, so it's a way of defining G of 0, then the solution decays like x to the gamma. And so these are the scaling solutions which correspond to the situations where gamma was between 2 and 4, where there was this different prediction. So by working with these solutions, we could also find that this differential equation has also the same critical behaviors when gamma is less than 4 than that was predicted. Okay, so we have these scaling functions. Now, let me just come towards the end and come to the last part of my talk and to say why the problem is related to the initial problem of deepening that I mentioned. Okay, so in fact, there is a hierarchical lattice version of the deepening problem. I am not going to go too much into the details, but somehow the problem can be summarized as a very simple mathematical problem. And the idea, so what I am saying now is not absolutely correct, but just it gives you the idea of it. But the idea is that instead of taking the model of deepening with loops of arbitrary size, essentially you allow loops to have only lengths which are powers of 2. So there is some kind of hierarchy that you can write. As a result, you end up with a very simple problem to formulate. And the problem is the following: when you have when the system size is 0, so essentially you have a single contact, and so the value at level 0 are just random variables, so the xi as it is here, and then you iterate the values very much like in the tree before, but instead of saying I take x1 plus x2 minus 1 and the max with 0, then now we take this recursion. So z at level 2L is written as with this formula with two independent realization of Zn. And B is a parameter there, which is fixed. And in fact, the question is, when the system size becomes very large, you would like to find f infinity, which is the limit of log of z to the z 2 to the n over 2 to the n. So you would like to know that. When you vary the initial distribution, then there will be a pin phase where f infinity is positive, f infinity is 0 in the n-pin phase. And in fact, the parameter b in this problem plays a role very similar to the parameter c that we had before at the beginning of the talk. So there are situations where it can be irrelevant or relevant and so on. Okay, so never mind. The really problem is mentioned, is formulated here, is that b is fixed. Say I take b equals 3, for example, or 4, or whatever, or a real number, and then I just start with some distribution of independent random variables, and then I build at level 2L the z by making some this nonlinear combination, which is simple, and then you want to know what is the limiting value of log of z to the n when n becomes large. Okay, so this is very similar problem. So why is it related to the problem I mentioned before? Is that if instead of working with z, you work with log z, then you find that log z, which I call xn plus 1 or xn, then will evolve according to some nonlinear function, and just taking the log of the recursion, the nonlinear function is here, it is in red, and here I compare it to the toy model. In the toy model, the recursion was just that you would take the max of the sum -1 and 0. So you had something which was flat if x was small enough, and then it would start linear. And the function g here is the red curve. So essentially, it's the same problem, except that you have replaced the red curve by the blue one. The toy model is just a simplification. In fact, if I remember, if you take B very large, the red curve will look very much like the blue one. So you can think of it as being either a limiting case or a simplification of the hierarchical model. But for the hierarchical model, as far as I know, we don't have the same as precise results. We don't know, okay, well, there is no proof that there is a Berezinski-Kosterlitz-Saules phase transition. Okay, so let me just conclude. So here we have, in fact, instead of concluding, it's more like open questions. So what we have looked at is this recursion for the toy model. And in fact, the results we have are valid only when the xn are integers, not because we don't think that they would be different when they are non-integers, but in fact, the proof relies very much on the fact that you know where the phase transition is. And in fact, as soon as xn is not an integer, we don't know where the phase transition is. So we don't know the critical line. Now, I tried to mention, in fact, this, my work was mostly in trying to understand this differential equation. I was surprised that there was so many solutions. You see, you have sum of exponentials, you have scaling functions, you have solutions which you should not consider because they correspond to negative measures and so on. But I would find very interesting to have really a full analysis of this equation. And in fact, you see, when you try to think about a problem, then you start to change something to see if you change something in the problem, whether you still understand it, or sometimes doing that, you understand better what you are trying to do. And in fact, at some stage, we played with the fact that we took the same equation, but now instead of having a convolution of 2, we took a convolution of 3. And in fact, somehow the critical value, instead of being when you have a convolution of 2, gamma, the change of behavior being when gamma is between 2 and 4. Here it was when gamma is between 1.5, and the 1.5 is rather easy to understand, to 2.6, and the 2.6, I have no theory for it. It's just numerical. I don't see when you have a convolution of 3, why there is a special value of 2.6. Now, you see, the thing, of course, which would be more interesting would be just to be able to extend these results to the case of the hierarchical model. Essentially, I think the precise expression of the function g does not matter. I think you should find the same result, whatever g has this kind of shape, but the precise formula is not important. And of course, it would be nice to have a proof that the same behavior is valid also for the Polancharaga model, which was the initial motivation. Okay, thank you for your attention.
Well, thank you very much. Okay. And it's now time for questions. So if you have some, please feel free to either raise your hand or write it down in the chat. And let's go.
You see, I'm not familiar with the chat, so you shouldn't.
Of course, I will read them out loud if there are some written. So maybe I will start with one question in case people are taking time to write or anything. In the first part of your talk, you mentioned this relevance or not of the disorder, and there was some parameter, and when alpha was getting past 3/2, there was something occurring.
Okay, yes.
Is there some way for people do not know well the topic to get some intuition why this 3/2 is popping, or is it really something?
Okay, so in fact it was for the parameter C, and okay, it's the parameter C, which takes the value 3/2, but in fact there is, okay, I did not write the name here, but okay, there is something very general, and which says that if you have a pure system which has a singularity like 2 to the minus alpha in the free energy, then if alpha is negative, then disorder is irrelevant. And the way that alpha is related to C, that's easy to do, is 2C minus 3 over C minus 1. So when C is 3/2, it's a place where alpha vanishes. And alpha negative, you expect that the weak disorder will not change the behavior between the pure and the random system, and alpha negative you expect is to change. And this is called the Harris criterion, which was shown in the 70s. So this is the Harris criterion. Now, to understand it, there are a number of ways. For example, if you make just a weak disorder expansion, so you say, okay, I have the pure system, and then I assume that I look for the correction, the first correction to due to a very weak disorder in the free energy. You find that, so this you can do when you are not at the phase transition. You are at a certain temperature, you make a weak disorder expansion. And what you would see is that when alpha is negative, then the correction when you approach the phase transition remains very small. And when alpha is positive, the first correction to disorder will become large and will somehow start to dominate the leading behavior. So that's a way to just by doing a very some perturbation in the width of disorder, you can see that.
Okay. Thanks a lot. It was yeah, very enlightening. Are there other questions? I don't think there were in the chat.
May I ask one question?
Of course.
So why is it more difficult if you go from integers to, let's say, half integers or something like that? I mean, intuitively for me, this is not, I mean, the distribution is then concentrated on another lattice, but why does it make so many more, cause so many more problems?
Okay, because you don't know where is the phase. You see, all these proofs. Okay, from the point of view of the differential equation I wrote and I discussed, the story is the same. So this differential equation would not see it. But if you want a mathematical proof, like the one that Zhan will mention, the thing that you need is really to know where is the phase transition. And the place where the phase transition occurs is given by this formula here. And if it becomes non-integer, then you don't know where the phase transition is. And because you don't know that, there are a number of things that the proof cannot achieve. So it's only for integers that this formula here with the h'2 and h2 tells you where is the phase transition.
Okay, thank you.
But it's true that it looks not so different. Yes.
Other questions?
Well, if I may, so is there some reason why the DKT phase transition occurs in the Polancharaga model, which is the same phase transition as the one with the XY model? Is there a connection between the two underlying models, or?
I don't think. Okay, you see, in the XY model, you have this idea of vortices and so on, and here I don't see anything which looks like these vortices. So the only connection I can see is that when we took, you see, in the in the XY model, what happens is that you write some renormalization group transformation, and essentially you have two parameters. You have one parameter, which is the strength of the interaction, and the other one is the chemical potential, or say the density of vortices. Okay, so these are the two parameters that you renormalize. And when you write this renormalization transformation, you end up with equations which are like the one I wrote here, like this one. So these two parameters, they get renormalized this way in the XY model. And here it's the same. So the renormalization equations are the same. But when I say that this is R is an exponential, I don't see why I would say that A is the density of vortices and B is the strength of the interactions. Okay, I know.
Okay, thank you. And well, if I can ask another question. So you had the model with Bernoulli with Bernoulli random variables, right? Where you're at lambda smaller than 1/5, there is no passing in the tree, and when lambda is larger than 1/5, you have passing. Do you have a way to understand where does the transition occurs, like in a finite tree? If you imagine that you have a real valued random variables that tells you when you add the variables on the leaves, can you express when you will see the first positive values at the root of the binary tree?
I'm not sure. First, there is a problem of echo or whatever.
Sorry, I have a bad mic. Yeah, I can try to write it down in the chat.
But I'm not sure. I think I got most of what you said, but I'm not sure I know the answer. Maybe Zhan knows it. I'm not totally sure. Okay, okay. Yes, I'm not sure I know the answer.
Okay.
I'm sorry, I don't know the answer either. Sorry.
No, go.
No, I have no idea about the question by Bastien.
Okay, yeah, sorry. It's okay.
Okay. Are there any other questions to ask? If not, I suggest we thank Bernard again. And we have a 6 minutes break, and we resume at 3 o'clock UTC. So we keep the YouTube diffusion open. So just everyone be aware that it's still being recorded and that it will remain online later. So don't hesitate to close camera on mic in case you don't want something to appear like that. I will just close the backup save, but the YouTube live is still active, as you can see normally. Yeah, maybe I will ask a question to Zhan, but it's the. So yeah, it's we are during the coffee break and so on, but the fact that I mean, this idea of having a tree and we combine the values of the two parents to get the one of the child and so on. It reminds me a bit of stuff like, I don't know, last passage percolation or stuff like that, but instead of doing it on Z2 or N2, we would do it on a tree, but not with a max function, but with a sum -1, and we truncate at 0. Like, is there any kind of familiarity between these two models, or just it's very, very different and I should not put them in connection in my mind?
Well, certainly formally they look somehow alike, but I fear that, I'm afraid that mathematically speaking, they are of different nature in the sense that the model Bernard was talking about actually was a dynamical system. All the randomness comes from the initial generation.
That's true.
Everything afterwards is deterministic. And somehow that's one of the main sources of difficulties. So once you know what happens initially, you know, theoretically, you know everything. So that's something I think a little bit special. Where otherwise, the same mechanism actually occurs in other models. For example, in the parking schemas studied by Christina Goldschmidt, by Nicolas Curien, they studied exactly the same recursion formula, but they have more randomness. I mean, the cars arrive not only from the leaves of the tree, but also, I mean, in the middle of the trees. And more randomness somehow gives you more room for doing things. Yes, I mean, from
I totally understand.
That's clear. Yeah.
Yeah, thank you very much for pointing this out, because it was a corollary of all the definitions and everything that was said, but I believe I didn't have enough awareness of this aspect of the model. Okay, thanks for stressing this point. It's really, everything is at the boundary, at the leaves, and okay.
Yes.
Well,
I'm making excuses for ourselves to have less results than Nicola and Christina.
No, but because otherwise I was slightly surprised, because since usually the tree is supposed to be easier than the square lattice, I was wondering, why the difficulties are okay. And now that I have the clear, exactly what you said, the fact that the randomness is just at the original generation, and then everything is just iterating. Okay. Really cool. Okay, thanks. Still have a bit less than roughly 1 minute before resuming.
So let me still point out that there could be a kind of a probabilistic connection with other things. At least quite a few years ago, Bernard mentioned that he thought the model would be a kind of dual to branching random walk with an absorbing wall or something like that. So it was a conjecture. So if that's true, then okay. I mean, branching random walk certainly is a lot more probabilistic, and it's not certainly not just a dynamical system, but we are very far from that.
I see. Checking the time. Okay, so since it's time, at least I will relaunch the backup save on the computer in case the YouTube link would die or something. I wait a few more seconds just in case people are a little bit late. And okay, let's say it's time. So I make the backup save like this. Okay. You can you share your screen?
Okay, let's see.
Great. Then perfect. Great. And okay, so I suggest we resume now. So for the second part of this talk on renormalization and disorder, we have the pleasure to listen to Zhan Shi from the Chinese Academy of Sciences. And I let you speak. Thank you very much.
Thank you, Sebastian. So first, I wish to thank the organizers for the invitation. It's a great pleasure to be here doing mathematics with everyone. So I wish to bring in a few mathematical notes to the content of the talk by Bernard. So since it's the same work, so we have exactly the same co-authors, Xin Chen from Shanghai, Victor Dagar and Yueying Hu from Paris, and Michel Lifshitz from St. Petersburg. Basically, most of the work was done when I was in Paris. Okay, so here is an outline. It looks like there are a lot of things, but actually the structure is very simple. So page 2 is the current page. And I will start by recalling a few relevant material from Bernard's talk, including a result which I call Theorem 1, and then I'm going to present another result called Theorem 2. And so I try to prove both theorems during the talk. And to do that, I need to prepare a few things. And the important thing which I want to mention is a kind of lemma which I call a claim. Then I come back to the statements of the Theorem 2, and then I will try to prove in 2 pages the claim, and then I will try to convince you that the claim will give us both theorems. But of course, these 3 pages are shameless cheating. I mean, it's not rigorous at all. Okay, so that's the outline. If you are ready, let's go. So here is the first of the 2 pages of the summary from Bernard's talk. So the model is recorded here. It's a sequence of random variables. We only care about the individual distribution of each of these random variables. And the law of xn plus 1 is defined as the law of the positive parts of the sum of 2 independent copies of xn, but I remove 1 from the sum. The initial distribution is not important. So you can take basically any non-negative distribution, but an important thing is it should be integer valued. We have already seen in Bernard's talk is that a simple example was the example of Bernoulli, well, twice Bernoulli. So if you don't care about the initial distribution, you just think about twice the Bernoulli. So x naught is 2 with the probability p, and is 0 with the probability 1 minus p. So by doing that, actually, I'm not going to discuss anything about the stable-like case, which Bernard described as the case when gamma is between 2 and 4, because here everything is bounded. So everything, well, we have all kinds of integrabilities. Okay, we have seen that Bernard defined the ratio between the expectation of xn and 2 to the n, and the ratio has a limit when n goes to infinity, and it's finite. This ratio, I'll call it free energy. The proof is very simple. because by definition, xn plus 1, if I remove the -1 in the definition, then things becomes larger. But an advantage is that both of them being non-negative, I can remove the positive sign. So if I take the expectation on both sides, then I get this very nice inequality, very simple, which means that this ratio actually is non-increasing in n. So the monotonicity allows me to conclude that the limit exists, which is necessarily finite, because at the beginning it was finite. I assume that at the beginning it was bounded. Okay, so that's the end of the proof of the lemma. There are a couple of consequences. The first one is that this limit thing, which I call free energy, is smaller than or equal to any element in this sequence. I mean, that's trivial because of the monotonicity. It's the decreasing limit of the sequence. Okay, so, and actually the same proof will give me another inequality, because instead of looking at the E of xn plus 1, if I look at E of xn plus 1 minus 1, then I'll get the same inequalities, but in the opposite direction, meaning that actually this guy as a function of n actually is increasing, well, not decreasing. So again, this guy also has a limit when n goes to infinity, has an increasing limit, which of course is again the same limit as the other guy, because -1, who cares at the end. So that gives me an upper bound and a lower bound for the free energy. The inequalities are valid for all n and for all p, of course. So that's a first consequence from the proof of the lemma. And the second consequence is that there exists a critical value for p. Well, in Bernard's talk, it was called lambda. So here it becomes p. There exists a critical value for p, such that when p is strictly greater than pc, then the free energy is strictly positive. And when p is strictly smaller than pc, then the free energy vanishes. And we have seen in Bernard's talk that actually at criticality, the free energy still vanishes. And an important starting point is the result by the team of Gollet, Ekman, Galazet, and Martin, who characterized the criticality by means of this identity. In Bernard's talk, it was written as twice h prime of 2 is equal to h of 2, but this is the probabilistic writing of the condition in Bernard's talk. Well, don't worry, I'm going to record it in the next page, and I'm even going to prove it. So this is from the previous page, and here is my proof. The proof is not exactly complete, but almost. So, well, we have seen the basic ingredients from Bernard's talk. So I write Hn to be the moment generating function of Xn. So this was the definition of our system. And I prefer to write it in terms of the moment generating function. And of course, the only thing which troubles me is this sign of positive part. And here we see that I only need to use really this positive part only when both of the random variables vanish. That's the only situation when I do need this positive part sign. Otherwise, who cares about this thing? Yes. And this is the place where we rely strongly on the assumption that everything is integer valued. So which means that if you use this proof, then it's crucial that everything is integer valued. Okay, once you are here, and then it's trivial, well, it's elementary to get this identity. And what's really nice with this identity is that the first fact on the right-hand side and the expression on the left-hand side, I mean, it's the same expression, except that here is for n plus 1 and there it was for n. So you can iterate the argument and then you get an explicit expression for this thing. It's the initial value multiplied by this, or the product of things. Okay, so we still need to do some honest work, but the most important idea is already here. So the idea was due to the team of Golay and his co-authors. So it means that if initially it's strictly positive, then the system will stay strictly positive forever. If it's strictly negative, then everything will be strictly negative forever. And if vanish initially, then it will vanish forever. So I guess everyone is already convinced that this identity, saying that this vanishes, characterizes the criticality, because the criticality of the system is at the frontier between supercriticality and subcriticality. So my proof is not completely complete, but I guess everybody is convinced that this identity tells you where to look for criticality. So a consequence of the proof is that at criticality, not only initially I have the identity, but I have this identity forever for all n. And this is something which is quite friendly in the rest of the talk. I mean, we do like this kind of identities, and that's very important for us. Okay, so there was a conjecture by Derrida and Hodo about the free energy when P is certainly strictly greater than PC, so that the free energy is strictly positive, but I let epsilon goes to 0, and the conjecture say that you should go to 0 sub-exponentially. And we have not been able to prove the conjecture from mathematical points of view, but only a weak version, in the sense that we are able to get this 1/2 exponent, but we have not been able to erase the small o of 1 in the power of epsilon. I wish to mention that this conjecture was rigorously proved by the team of Hu, Malin, and Pan last year for a continuous time analog of the model. There will be a few other conjectures coming in the next pages, and all the conjectures have been proved rigorously by the 3 authors, but for their model. And it's not clear how to adapt their methods to our model. Okay, so I told you that I wish to present another results, and I start with a conjecture. So that's another conjecture by the 2 teams independently, by the team of Golay and by Derrida Hodo independently, meaning that with different approaches, but they arrived at the same conclusion, is that at criticality, if you take P to be PC, so in the example of Bernoulli, PC is 1/5. That's what we saw with Bernard in the previous talk. So at criticality, the survival probability would go to 0, and it should be equivalent to 4/n squared. Equivalence meaning that if you take the ratio, the limit should be 1. Well, the conjecture is still open, but it's not very hard to prove that at criticality, the expected value of xn is a capital O of 1/n when n goes to infinity. Capital O means that if you divide the expectation by 1/n, it's bounded in n. If you admit this, then by Markov inequality, xn is integer valued. No, I don't even need that. This probability is certainly bounded by the expectation. So you get something which says that the probability is a capital O of 1/n. So it's still very far from the conjecture, but we do get something. At least we know that it goes to 0. And for several years, we have not been able to replace this capital O by small o. Well, the proof of this it's incomplete as in the previous proof, but the first step is to say that xn is bounded by 2 to the xn minus 1. And the expectation of this second thing is it is possible to estimate it. It turns out that this expectation is capital O of 1 over n, and this is optimal. It's greater than or equal to a small constant over n for O n. So if you compare this with the conjecture, it means that the first inequality is too rough. It's certainly trivially valid, but it's too rough. Okay, meaning that we are never going to be able to prove the conjecture by starting with this inequality. Okay, our conjecture is that the expected value of xn at criticality would be equivalent to 8 over n squared. So it's in agreement with the conjecture on the survival probability. So here is another result from us. So we prove that, okay, the square, the power 2 is the correct proof, but we still have a small o of 1 in the power of n, which we have not been able to remove. This means that concretely, there are important mathematical things in this system which we have not been able to understand. And I recall the statement of the first theorem. So I wish to prove both theorems in the talk, and because there is a common tool which is called open subtree, where the proofs of the two theorems are very, very different, but both of them, both proofs rely on studying the open subtree. So let me introduce the open subtree, and before doing that, I first need to present a very intuitive hierarchical representation, and that was already in the previous work by Gollet and his co-authors and by Derrida and Rodot. So let's first look at the circles on the first line. So there is an infinite sequence, so you see the 3 dots, right? So it's infinite. It's an infinite sequence of circles, and each circle represents an individual in the system. So each individual has a special value, and which is in the initial generation, it's a random variable with the distribution of x naught, and all these random variables are assumed to be independent. And then everyone in the initial generation gets married with one of the neighbors, and they get a unique child. So all these children are going to form the individuals, the population in the first generation of the system. And the children are going to do exactly what their parents did, meaning that each of them marries one of the neighbors. And again, each couple is going to have a unique child. And these new children are going to form the individuals in the second generation, and so on and so on. So in my picture, this is initial generation, the first generation, second generation, and in the third generation, in my picture, there is only one individual, but of course it's an infinite sequence and so on. So n is 3 in my picture. And the rule is that if your parents has money, the amount is A and B respectively, and they are going to give you the entire, all their money to the unique child. So the child receives the total amount of money from the parents, but he pays a unit amount of money to the government as a kind of income tax. Except that when both A and B vanish, then the child doesn't receive anything, then he is not going to pay income tax, which is fair. Okay, so you see that this very natural representation, actually, it is equivalent to our system in the sense that all the random variables in the first generation are IID with a common distribution x0. Oops, sorry, excuse me. All the random variables in the first generation, they are also IID having the common distribution x1 and so on. So on each line, the random variables are IID having the common distribution, which is what you want. Okay. So once I draw the picture of the hierarchical representation, then I'm able to introduce this technical notion of open subtree. That's really my goal. So look at the first n generation. So I take just I fix a vertex in the nth generation, and then I look at the 2 to the n vertices in the initial generations. From each of the vertices in the initial generation, there is a unique path from this vertex to the bottom vertex. Yes, so the total amount of passes to the nth generation is 2 to the n. And I only care about those passes among the 2 to the n, which are called open. And by open, I mean that along the path, everybody pays the income tax. Mathematically speaking, it means that along the path, I don't need to do the positive part operation, because doing the positive part operation means that you don't receive anything. That's why you don't need, and that means that you don't pay income tax. So I only care about those passes which are drawn in red in my picture, along which everybody pays income tax. But it's possible that someone vanishes. That's quite possible. I mean, it's possible that you get nothing. Well, you have value 0, but you marry someone which is very rich, and then and this someone still allows you to reach the bottom vertex. That's quite possible. Just like in real life, even if when you were born very poor, if you are lucky to marry a rich person, then you still can stay very rich. And here it's the same. So it's possible that the initial value is 0. And my picture actually is wrong in the sense that if initially this guy is red, for sure that the neighbor must be red because their child is common, and by assumption the child is red, then this guy must be red. Okay, so my picture actually is wrong. And I count the total amount of, the total number of such red passes until generation n, which I give it a name capital N. And the claim, that's the only technical part in my talk. The claim is that for one, we are going to see very quickly that the probability that capital N is positive, actually this probability goes to 0, meaning that it's unlikely that you see such a red picture. But conditionally on its existence, then the number of red branches is approximately n squared. That's what I'm going I'm trying to convince you. So first, let me convince you that this event actually is unlikely. So that's my next, and that's very easy actually. Saying that we do have some red passes is exactly equivalent to saying that the two parents of the bottom vertex, they give something to this bottom vertex, meaning that the bottom guy pays income tax. That's equivalent. I mean, it's exactly the same event. And then you can write this probability as the difference of these two. And since we already knew that at criticality, the probability that xn is strictly positive, it goes to 0. Actually, we even know that it's capital O of 1 over n. So which means that the second expression actually is negligible compared to the first one. So it's equivalent to the first one. So actually, at criticality, this probability and that probability, they are equivalent, well, with a constant multiple 2. Okay. So initially, the statements of theorem 2 was that, but now I'm going to forget about its statements. Actually, the correct statement is that at criticality, the probability of the existence of the red subtree until generation n, this probability is 1 over n to the 2 plus small o 1. And it's this thing which I'm going to prove. Okay, so now I wish to convince you why the claim is true. So here is my so-called proof of the claim, but it's not a full proof. So I can extend the notion of open paths to any vertex in the subtree. So for any vertex u, I can count the number of branches, open branches leading to u. I don't care about what happens afterwards. I only count about the number of open branches. They are open until u. Okay, and then I can write a recursion formula for this number. Actually, it's the sum of the total number of open branches leading to the parents, but under the condition that I do receive something from the parents. So this is important. So the first line is just the definition of our model. So it means that I have an analytical expression for the pair, the spatial value and the number of open branches. So I can write a recursive formula for the joint moment generating function of xn and capital N, exactly as what I did a few pages ago for xn alone, but now I can do it jointly. So the formula is a little bit more complicated, but okay. Oops, something, okay. I'm not going to write down the explicit formula, but what I care about is only this expression, which is the partial derivative with respect to the t. Okay, let me come back to the first one. If I look at this joint moment generating function and I differentiate with respect to t, and at point t to the 1, I get exactly what I call as an of s. And it turns out that there is also a nice recursion formula for this expression. Here, hn is as before the moment generating function of xn. And to get this identity, I used the important fact that at criticality, actually, the derivative here at point 2 is half the moment generating function at point 2. So I need to use this to get this identity. Well, I don't show you how I get it, but the proof is elementary. I mean, using this identity. Once you are here, we are exactly in the same situation as before because we get the same expression here. So I can iterate the identity. So at the end, I solve the equation. And actually, we meet exactly the same factor, the blue factor, which is the product of moment generating function at 2. And of course, the thing I'm looking at, actually, I can write it as, I mean, in a more probabilistic way. I mean, so these two equalities are identical, and capital N naught by definition is simply 1. So I have an identity saying that this thing is that thing. And now I use something which we have learned from from the team of Golay and his co-authors. So it was proved quite a long time ago. So they were able to prove that the second factor, the blue factor, actually behaves like n squared when n goes to infinity. And on the left-hand side, it's almost the expectation of capital N, except that we have a density. But this density, actually, the expected value is approximately 2, because this was our famous characterization of criticality. I mean, it was known to the team of Golay and his co-authors. And this thing, if I write it as 1 plus the difference between this thing and the 1 and the second term, we know that it goes to 0. Actually, not only we know it goes to 0, we know that it's capital O of 1 over n. Okay, so it means that actually the density here on the left-hand side, the density here, the expectation is approximately 2. So here I'm cheating. I say that it's as if the density is of constant order, so that on the left-hand side is more or less the true value of capital N. On the right-hand side, we know that it's a constant multiplied by something which is of order of magnitude n squared. So that's why I allow myself to say that capital N is approximately n squared. But of course, things are not as simple as that. This is very heuristic. So mathematically speaking, we are not able to get rid of this small o of 1 improbability under this conditional probability. But I hope it gives you some feeling about why there should be a kind of n square here. Okay, so I reach the last mathematical page. So now I hope I have convinced you that the claim was true. And from the claim, it's more or less easy to guess the statements of the theorems. So let's first try the second theorem. So the statement is here. So the claim tells us, well, not exactly in this form, but I hope you agree that capital N, if there is something in the open subtree, then the number of leaves is approximately n squared at criticality. On the other hand, the expected number of the leaves in the open subtree is of constant order of magnitude. Actually, the two lines give you some feeling like it looks like the open subtree, it looks like a critical Galton-Watson tree. If you think about a critical Galton-Watson tree, at criticality, we know that the expected number of individuals at each generation is a constant. It doesn't change. But it doesn't survive. So it's very hard to survive until generation n. But and the survival probability is roughly speaking 1 over n, when assuming that the variance is finite. But when you survive, then the number of individuals is approximately n, where n times an exponential random variable. And here there is something very similar. So typically, the effective value is just a constant, and typically it doesn't survive. But when it does survive, then the number actually is the inverse of the surviving probability, because the surviving probability, you see, is the ratio between the two things. The numerator, we say, is of constant order, and the denominator is approximately n squared. So that gives me the order of magnitude of the survival probability for the open subtree. And again, this is not rigorous, so we are not able to get rid of the small o of 1 in the power of n. Okay, so that was the theorem 2. theorem 1, actually, I will only care about the lower bound. Somehow the upper bound is easier, but it's not very probabilistic. Personally, I don't like the proof of the upper bound very much. I really enjoy the proof of the lower bounds. So it goes as follows. Claims tells us that if the open subtree does survive until generation n, for the moment, let's forget about the exponents in red, 0. Conditionally, on the survival, we know that there are approximately n square leaves at criticality. And instead of counting the number of open passes, I count the number of open passes with initial value 0. We know that it's still possible to count such the number of such open passes. Maybe you still remember the story of a poor guy, well, a guy born poor, but who marries a rich person. And I'm interested exact in this situation. Initially, you have nothing, but thanks to your neighbors, you still manage to survive until generation n. And it turns out that if there are such guys, then the number of such guys is still approximately n squared. Well, it's not, it looks like it's the same conclusion as without this superscript. But, well, that's because my writing is not very rigorous. Actually, there should be, well, that's a conjecture, there should be a limiting distribution, then the limited distribution will be different. Okay, but anyway, so that's the idea. So assuming that there are guys born poor, but they managed to survive, then the number of such guys is approximately n squared at criticality. So now I look at this number, which is n squared, such guys born very poor at the beginning. They have nothing at the beginning at criticality. But now I look at probability, which is PC plus epsilon. So the probability P is increased by epsilon. So among these n squared guys, there should be approximately n squared times epsilon of them who, instead of 0 at the beginning, they have values strictly positive. So at least 1, because everything is supposed to be integer valued. And if I look at the expectation of xn and when P is PC plus epsilon, I only care about these things because a tremendous advantage of looking at the open subtree is that along all the branches, there nowhere you need to take the positive path. So if you increase the initial value from 0 to 1, then this 1 is going to show up at the bottom. That's a crucial point. And that's the reason for which I'm interested in this open subtree. So I only care about these guys. Initially, they were born nothing, but they managed to be open until the nth generation. And then these guys will give me a lower bound for xn. So I take the expectation and we say that, okay, it's more or less like n squared times epsilon. And this is true for all n sufficiently large, and I take n to be 2 over square root of epsilon. Actually, it should be larger than that. Then the expected value should be at least 4. And I hope you still remember that we had a very simple upper bound and a very simple lower bound. Here I use the lower bound for the free energy for all P and for all N. And I take P to be PC plus epsilon and N to be N epsilon here. And the numerator is, we say, is at least 3, and the denominator will give me exactly what I was looking for. Well, here, formally, I only have 1/2. There is no small or 1, but I told you that I was cheating. So at the end, we get small O of 1 in the power epsilon, and that gives me the lower bound in theorem 1. Okay, so that's more or less all the mathematics I wanted to show you. And here is, oops. Let me move to the next page. Okay, so I think I'm going to leave this one and come back. Oops. And then this is my last page. So if I look at the set of all the open subpasses, actually it's a subtree of the binary tree. The height is n, and the number of leaves is capital N. So the surviving probability at criticality is conjectured to be equivalent to 8 over n squared, and that's still open. We also conjecture that this subtree conditionally on the survival, if properly normalized, meaning that divide the height by n, it divided the values by n, it should converge in some sense to a continuum tree, which we call capital T. And we have not been able to prove either, but it's possible to describe this tree, this continuum tree, and it has been proved by the team of Hu, Malan, and Ban. For this continuum tree, it has been proved that asymptotically, if you count the number of leaves asymptotically, there should be a four-dimensional Brownian motion hidden in the number of trees. Well, in the form of a four-dimensional Bessel bridge. So it means that if we are sufficiently clever, in principle, hidden behind this picture of open subtree, there should be a four-dimensional, asymptotically, there should be a four-dimensional Brownian motion somewhere, but we have not been able to prove that. And the proof of by Hu, Malan, and Ban for this continuum tree actually is analytical. I mean, it's computational. It doesn't explain why there should be a four-dimensional Brownian motion. So there are a lot of mystery with this model. So in addition of what Bernard presented us, so we have all kinds of open problems for this model. Well, thank you very much.
Thank you. So first, a round of applause. And yeah, if anyone has a question, please feel free to raise hand or ask it in the chat, or you can unmute yourself also. So in case people are writing or thinking of their question, I will ask. No, there is. Oh, it was a thank you in the chat from Yuyun. Yes. So I have a few questions. One of them is, so from what you said of related works, it seems that continuous time is easier or less difficult than discrete time. Some questions seem to have exact solutions in continuous time and not in discrete time. Is there a way to understand why continuous time is easier, even though the continuous time model, you didn't define it exactly, but can we get a feeling for that? Or?
Yes, actually, you can guess how it looks like, the model and the solution. If you think of our model as just a one-dimensional simple random walk on the line, then the continuous time model it's more or less, well, it's not exactly true. It's more or less like Brownian motion. So for Brownian motion, somehow you can do some exact computation, but by the team of Hu, Malin, and the Ban, their exact computations were done by solving some PDEs. Well, we know that Brownian motion also is certainly related to PDE, to the heat equation, for example. So somehow you can think of the work by Hu, Malin, and Ban just like solving a heat equation for Brownian motion. And then we have trouble to adapt their method to our random work because we don't know how to manage to have some nice PDE or discrete PDE to which we are able to say something. I mean, we have not been able to do anything of the kind, even though we believe that we understand a lot of things. Well, things were understood a lot, even in the original paper by Derrida and Hodo, I mean, 7 years ago. So Bernard explained a few things to us, so he presented us. So the PDE by Hu, Malin, and Ban was more somehow like the convolution equation Bernard presented to us. It was not exactly the same, but well, somehow of the kind. So I think even though I didn't say a single word about the exact form of their model, the exact form, their method, but I think you can imagine how they look like.
Yeah, totally. So thanks a lot. Are there questions from other people? I still have a couple, so I will ask them. So yeah, it's maybe a question more about the okay. Maybe more a question about the definition of the model rather than how to solve it. This formula A plus B minus 1 positive part. So it is very, very natural from a point of view of legacy from parents to children, as you explained. But from a physical perspective, what are the nice properties that this function is capturing? Like this summation we remove, which we take positive. Why has it been chosen?
Oh, well, that was actually, that was more or less explained in Bernard's talk, because we choose this one only because we want to have an exact representation of our model. I mean, if I want to study this model, then I don't have any other choice but this one. Otherwise, this representation will not be a hierarchical representation of the system. So if our system was not defined differently, then of course I'll get a different rule. But the rule here is only to be fit to our model.
Yes, but my question then is why this model? And but maybe I see Bernard put the camera on, unmute himself.
Yeah.
So yeah, why in the initial model all the representation? If we take just the sum, it's easier, but not very interesting, I guess. So here we take the sum, we remove one.
Okay, if you would take only the sum, then it would be trivial because it would become a sum of a very large number of random variables, so you would get a Gaussian. Now, you see, giving talks and so on, it seems to me that you can think of a large system composed, you break a large system into two subsystems, and I don't want to be very precise about the system, but usually you say if you have two large systems, and the free energy of the two systems, you add them up, but there is small effect, just when you put them together, there is something. a small contribution. And so this -1 is maybe one of the simplest situations where you say, I take two subsystems, I group them together, and there is some interaction just at the boundary. Just when you put them together, okay, you can put -1. I don't know, I am not sure, for example, if the -1 was replaced by something random. I don't know, I think probably the story would be not so different. I don't know. That's for the coming 10 years, something to do.
Yeah.
No, but okay. But this is, you just add 2-3 energies, and then there is some small effect due to the boundary.
Okay, now I understand yeah, how it can come from physical situation. Okay, and I suggest maybe, except if there are questions from other people, that maybe we call it a day and we close the session now, and we can stay at the coffee break for a few additional questions with the speakers. So first, a last round of applause for Bernard and Zhan.
How do you give the coffee?
So coffee break without coffee.
With the button I should push to get the coffee?
Yeah, I'm sorry, it's not possible to upload or download a coffee yet. So I don't know if, yeah, if some people can only see this on YouTube live, maybe I should leave it open for these people. Yeah, so thanks again a lot for the talk. I had a couple of other questions, but oh no, before people leave, I wanted to make an announcement. So I should have said it earlier. So yes, two things. First, the next talk will be in 2 weeks by Adrián González Casanova and Sandra Palau about branching. Sorry, I'm not able to speak anymore. About branching processes forward and backward. And the second things I wanted to say is if in your country there is a change time from summertime to winter time or something like that, recall that it's at 2 p.m. UTC. So just look for change time between UTC and your local time in such a case. Okay, so now people can leave whenever they want without missing information about the webinar. And yeah, if I may, I would like to ask a few more questions. One of them is if additionally to the current model, we add some extra layer of randomness. So for example, instead of a binary tree, it gets a Galton-Watson one, or at each vertex, instead of having this a plus b minus 1 positive part, we have some local randomness in the value of -1 or something like that. If we had something like this, are there interesting things to say? And in particular, if we think of this perturbation as small and as if it was an external field in Ising or something like that, is there something interesting to say along these lines, or it's not a good way of asking questions?
Bernard can answer, yes.
I don't know. I think there. Okay, I remember there were some discussions about having a branching, the branching not being regular. You see that you have a certain distribution of branches or things like that. So certainly, for example, okay, one thing when there is no extra randomness, but for example, instead of 2 branches, there are 5 branches. The story is exactly the same. Yeah.
Yes, so if instead of a binary tree, if you look at a regular tree, then everything, goes on, and you still get this 1 over n square story for the survival probability. Okay, the criterion for criticality by the team of Golay and his co-authors doesn't change. It's still valid, where you add something depending on the number of children for each vertex, but otherwise it's the same proof. The survival probability and so on, everything is more or less identical, and maybe it could be a little bit surprising is that you always get n squared. The square doesn't depend on the number of children in the tree. It's the same for all regular trees. But I think there should be a whole bunch of new things to say, but we have not been able to do is to look at Galton-Watson tree. Somehow it's very strange that for Galton-Watson tree, we have not been able to say anything, literally anything. So the criterion of criticality by Golay and his co-authors breaks down, and that's the main trouble. You see that everything in our approach relies on the criterion. So if we don't have the criterion by Golay and his co-authors, then we are not able to do anything. And that's the case with the Galton-Watson tree. So that's very unfortunate. I think mathematically speaking, the next step should be to look at the Galton-Watson tree, but we have not been able to do anything towards this direction. And the -1, if you add some randomness. So instead of -1, you have -1 with some probability and don't do anything, -0 with another probability, then it's very easy. But that's the only randomness I'm able to do. If instead of 1 and 0, if I take 1 and 2, then I'm not able to say anything, because -2, as Bernard explained to us, we have not been able to do anything.
Yeah, because of the equation you mentioned,
yes.
the minus stuff squared. Yeah.
Yes. Well, we can cheat, assuming that X0 is supported in the subgroup 2 times. Okay. But otherwise, I don't know whether Gerhard was still here. Maybe Gerhard would be able to say something. No, okay, he is gone. Yeah. At some stage, I saw that he was able to say something well, but no, he's gone anyway. Okay, then I'm not. Don't know anything to say about non-regular trees.
Okay. Yeah, if there are other people who want to ask questions or chat, it's possible. I could again ask questions, but maybe it's better if, in case other people want to speak. So in the chat, you were thanked by several people. People were happy with the talk. So if you don't read the chat yourself, just be aware. Okay, maybe I will conclude with my 2 last questions quite quickly. But when you say there is a hidden 4-dimensional Brownian motion, what you mean is we can compute in terms of theorems or conjectures, depending on the model, some probability, and it turns out the formula is exactly given by the probability of something for 4-dimensional, but we don't know how to couple these objects. That's it?
Exactly. Okay. It's just a computational. So you count the number of leaves. At the end, you realize that you get exactly the same distribution as the one for the 4-dimensional Brownian motion. But okay, that's just computation. It doesn't explain you why there should be a 4-dimensional Brownian motion.
Yeah, a bit like the question of Bastien in Bernard's talk when he he asked, oh, there is this exponential minus 1 over square root. Does it mean there is a connection between depiling
Yes, sure.
the model of BKT? Well, it's the same universality class, but there is no coupling to the best of. Okay.
Yeah, but okay. To Bastian's question, I mean, the answer is not clear. I mean, it could be pure coincidence. I mean, I don't know how to think about this kind of things, but for the case of four-dimensional Brownian motion, I'm convinced that there should be a way to take it out, because four-dimensional Brownian motion, it should not be there just by accident. No one believes that.
Yeah.
Wherever you see a four-dimensional Brownian motion, there must be a reason. I mean, that part is clear to me.
Yeah, I have the same feeling, even though I don't know anything. But in terms of guts, it's the same. And my last question was about your theorem 2. At some point, you decided to change the statement from xn to nn.
Yes, yeah.
Does it mean that the original theorem is not proved on the one that is proved is with nn, or both of them are true, but you wanted to prove the nicer one? Like
both of them are true. Both of them are true, but somehow the original statement was more natural because it concerned the survival probability of the system. But for me, mathematically, it's more interesting to look at the survival probability for the open subtree. For me, that's the essential. So that's why I prefer to the new statement. But otherwise, the two statements are equivalent.
Okay, very nice. Yes, sorry for keeping you with my questions answered. I try not to prevent anyone else from asking questions, but it seemed I was mainly. So I can stop talking, and if anyone in the audience wants to discuss or anything, it's of course possible.
Hello. Hello, Zhan. Hello, Perla. Just to say hello to you.
So you are in
Thanks for
California?
the talk.
I will close the YouTube session just now.
Okay.